Good evening, everybody. It's March 22nd, day 5 of COVID-19 instruction, and welcome to Vex Labs, home of the mad scientists, virtual experiments by the Eliezers. This evening, we are doing diffraction of light. What happens to light when it passes a corner? Observe, if you please, the ordinary laser pointer. It's a circular aperture. It's a green light. Aim down. And it's a circle. Now, what happens to that light when it passes through a really big hole? Let's see, youth shine, a light, it's a circle, through a circle, and son of a gun, it's still a circle. Beautiful, all right, that wasn't so hard. Now, let's see what happens when you shine light through a much smaller circle. If we were in class, I would hold this up and say, see, this is the tiniest set of slits that money can buy. These slits are so fine, I could not scratch them even with a pin. I paid $50 for a piece of black plastic with holes in it. I would do the old nothing up my sleeve trick. I would hold this up to the light, and you'd see that this is a large rectangular window with a very, very fine black line in it, a fine black scratch, just like the thing you called obstacle in your virtual ripple tank. So we're going to set this up. I'm going to shine the light through the nice clear window. There it is. It's the light. It's kind of speckled because the air quality in here, and here I've hit that obstacle. Spot on. Do you see the streaks? Do you see the tiger stripes? Green and black and green and black. That is diffraction. And you'll see it more dramatically when we get to a single slit. Shine a light into a rectangle. Black plastic, clear rectangle for the light to go through. What do you see? Whoa. Not only do you see the circular spread, but you see that tiger stripe band across the middle. One really, really, really bright spot in the middle. We're going to call that the local maximum. Around it, we've got local minima. See those dark stripes? That is destructive interference right there. Light plus light equals dark. And the brighter stripes next to it are the local maxima. Let's go for 2D and see if we can make it more dramatic. This is a plain circular hole. Shine light through a plain circular hole. Only difference between this and the notebook paper is that it was very, very small. And holy cow, look at those rings. Maxima, minima, constructive interference, destructive interference, whining lab assistant in the background who does not wish to be put to bed when we're just getting good. Now we'll try it with a square. Square hole, beam of green light. What do you expect to see on the sheet? See the local maxima and minima? We've gone 2D this time. We've got these two big streaks of constructive interference at 90 degrees and destructive interference going all around. Now my favorite, everybody's favorite. Let's try it with the hexagon. There we go. Let it go, let it go. Let us all go out and play. Let it go, let it go. It's COVID-19 today. It's wickedly awesome. What was the difference between those holes that I shined the light through and these holes? Only one thing. They're smaller. Head over to the online Ripple Tank and follow the examples there to see why, when light passes a corner and misses by a good 200 nanometers, we get these awesome stripe patterns. Now, do your lab at falstad.com/ripple. When you're done, if you want to press play to check your results and get some keys to the menu, then press play. Also, you'll find a couple of real-life demos of diffraction at the end of the lab. Carry on. All right, so head over to the online Ripple Tank. If you want to change the color, crests are one color, troughs are the other. I happen to feature this one, and if you want to know which one is which, check out the 3D view, and you can see that light blue is crest and dark blue is trough, and traditionally one does stop a good deal of time. This is not called the seizure app for nothing. But once you get there, you'll be examining the 4 setups in your lab. Start with, head on over to your first example, which is half a plane. A plane wave is a wave that simply has a front and a back. It moves in a straight line fashion, as you can see. Regular waves moving forward until they hit that wall. What happens to the waves that hit the wall? We know that. They splash. You can see the splashes all over here. Check it out. Up and down and up and down. But if they don't hit the wall, what do?
They bend around in a circular motion.
Check it out. Even when the wave wasn't a circle, they bend around in a circular pattern. Do you see anything else kind of weird over here?
It's got like some weird like intersecting.
Yeah, it's got these weird streaky things in it. Those definitely bear more investigation. Head over to the second example, which is an obstacle. Pause. Press play when you've seen everything there is to see. Ready? Check it out. What happens when the waves hit the obstacle? Well, that's easy. They reflect, they splash, same as before. What happens when each one gets to the side of one corner?
It curves around.
Have those waves crashed into each other yet?
Not at this point.
Why not?
Because they're not close enough to crash.
Okay. Sooner or later.
They're going to.
We've got 2 variables here. One is enough time. Notice I stopped the experiment. The other one is enough space. If we made this a whole lot wider, we'd need more time for the waves to get around it. See? Aha, there we go. Now they're spreading quite a lot, but they don't seem to be interfering. They don't seem to be hitting each other or getting in each other's way. Now, let's give them enough space and enough time and see what happens. Hypothesize as to what's going to happen when the wave that's spreading around from the left meets the wave that's spreading around from the right, and they kind of interfere with what each other's doing. There they go. Hey, check it out. It's those streaky things again. Everybody see the destructive interference? Good. Everybody see the constructive interference?
Whoa.
Don't forget about that.
Whoa!
Check it out. Crests and troughs, higher highs, lower lows. We've got constructive and destructive interference when diffracting waves, waves that spread around corners in a circular pattern, spread so far they meet a wave coming from the other side that's doing the exact same thing. Now that you know what diffraction is and why diffraction will usually lead to interference given enough time and enough space, now we're ready for the great classic. We're looking at the single slit and the double slit experiment. We've got a plane wave here. Notice they don't give us much space to observe the plane wave. Before we get to the really interesting part, it hits a wall. Splash, reflect. Not much to do there. But in the wall, there's a single slit. Notice the slit has 2 corners, and the corners are very close to each other. Ready? Aim. Hypothesize. Predict what's going to happen as the wave spreads around the corners. Observe everything there is to observe. Answer the questions in your lab. Press play to check your work. This is an area of constructive interference. Higher highs, lower lows. If indeed this is a light wave, this is going to be very bright. We're going to call this the local maximum. Right around it are very, very dark streaks. Let's lower the frequency so you can see them a little better. The dark streaks are the local minimum. The light is going to be darker there because crests are hitting troughs and canceling out. Ask yourself, if there were more corners, if it were a double slit instead of a single slit, and those corners, as you can see in this particular example, were even closer together, would you expect more interference or less interference?
More interference.
Why?
Because there are more waves coming to interfere with each other.
Could you think of a way to set up a double slit so that although it was still two slits, it'd be less interference?
The farther apart that you put them.
Okay, so if I were to put two very narrow slits very far apart, then that would minimize the interference between them?
Yeah, although it doesn't seem possible.
Play around with your walls here. Notice you've got an add menu where you can add all sorts of lovely things and edit what you've added. Play around with seeing how you can work double slit interference here in the simulator. When you're done with the simulator, head over to the Young's double slit interference simulator and use the controls to see what these patterns are going to look like on an actual screen full of light. Lights. You can see diffraction through windows, windshields, screens, and curtains, anywhere that there are thin, fine slits with corners aplenty. Check it out. If you're looking through glasses that are even slightly scratched, or looking through a very sheer curtain or a screen, the light will be diffracting around the edges of the scratches or the threads in that wonderful sparkly pattern that artists are so familiar with when they make those crosses and X's to show how little stars are twinkling, twinkling.